All right, pre-cal 12, let's get after it. Here we go, video number 20. We are talking exponents. We're going to dive from exponents into logarithms. So it's important to tie down our basic exponential knowledge again with respect to operations with those exponents, and then again graphing our basic exponential. So let's just do a quick review of all of our exponent laws from years past. So anything to the power of 0, and bear in mind that there's no negative signs in front of any of these. So anything to the power of 0, no negative in front, is just 1. If you have power to a power, so x to the power of a and then all to the power of b, we multiply the exponents, so it's a times b. And then here, if you have power, technically this is still power to a power, but each of the powers on the inside is a 1. So you got to multiply the a into both. So we end up with x a y a. And now multiplying a common base, we add the exponents. So not that. X to the power of a plus b. Dividing a common base, we subtract the exponents. Not that. So x equals a minus b. If you have a negative exponent in the numerator, it becomes a positive exponent in the denominator. And it's worth noting really quickly that if you have a negative exponent in the denominator, well, then it just becomes a positive exponent in the numerator. So basically switches where your base is, either numerator or denominator. And you'll see that in this example here, because technically that's x to the negative a and y to the negative a, but we can also just flip the entire fraction first, change it to a positive exponent. That is the same as going x to the negative a over y to the negative a, because then you would have y to the a over x to the a. We get the same thing here. And then lastly, if you have two bases that are the same, this is a very important rule, then A has to equal B, okay? Otherwise, those statements wouldn't be equal. So if you can get the same base, then you can just compare the exponents, and we'll see that in action shortly. So here we go. Simplify these using our rules. So first thing to look at is I don't have a common base, but you'll get to the point where you're a little bit more quick with identifying the fact that both of those bases are able to be written to the power of 2. So let's do that. 4 is just 2 to the power of 2, and then all to the power of 3x plus 7. And 8 is 2 to the power of 3, and then all to the power of 2x plus 5. But now we can go power to a power. So we have 2 times that whole thing, and we have 3 times that whole thing. So what do we get now? We get 2 to the 6x plus 14 over 2 to the 6x plus 15. So what does that give us? Well, now we have a common base and we are dividing, so we subtract the exponents. So we'll just do that up here. This is just the exponents that I'm subtracting. Remember, you're subtracting everything. So you end up with 6x plus 14 minus 6x minus 15, which gives you negative 1. So we end up with 2 to the power of negative 1, which is just 1 over 2 to the 1. So we've used all of our exponent laws there, quite a few of them. So again, on this next one, similar thing. 9 is the same as 3 squared. Oh, wow, I'm on fire today. 3 squared. And we do that, and then to the power of 2 minus x minus 5. And then 27 is 3 cubed, and then to the 2 minus x. So again, power to a power, this times all that, and this times all that. So we end up with 3 to the 4x minus 10 equals 3 to the 6 minus 3x. And now we're at that moment where the bases are the same, so the exponents must be equal. So now we can just compare the exponents. So 4x minus 10 equals 6 minus 3x, and now it's grade 9 algebra. Add 3x to both sides. 7x, and then add 10 to both sides, equals 16. And what do we get from there? We get x equals 16 over 7. Now let's just double check here, make sure everything went according to plan. Boom, boom, looks good. So we've solved for x. So anytime you have well, until we learn about logs, anytime you have an unknown in your exponent, if you can get the base to be the same, then you can just compare the exponents, and that's a good way to solve for an unknown in your exponent. Okay, so how about exponential graphs? Well, if you recall an exponential graph, for example, y equals 2 to the power of x. Well, every exponential has a defining characteristic, and it's this one. Without any sort of transformation, it goes through 0, 1, because anytime x is 0, 2 to the power 0 is 1, 3 to the power 0 is 1, so on and so forth. And then we're looking at points that exist on my graph. So here you can see that we're going to increase exponentially. As x increases, our y goes up. Now, I can't actually pinpoint this because that point doesn't exactly cross at 2 and that point doesn't exactly cross at 3. So, but you'll see in the next example that that's what we're looking for. Now, this statement is what matters though. If my a value is greater than 1, means my base is a whole number, then I'm an increasing function and I start from 0 on my x-axis. I go up really fast because my base is a whole number and I'm increasing exponentially. But you'll then notice that I also, as I go into the negatives, I get infinitely close to 0. And why is that? Because if you have 2 to the power of -1, remember that's just a half. 2 to the power of -3 is just a third. 2 to the power of -4 is a quarter. So you can see I'm slowly getting closer and closer to 0. When you get 2 to the power of -1,000, right, that's 1 over 2 to the 1,000, which is a very, very, very tiny number. So you can see that we're getting infinitely close, but never touch 0, because there's no exponent, there's no x value for an exponent that will ever give me that. So we get what's called a horizontal asymptote here. We don't actually touch the x-axis. And that is an increasing function. Now you'll notice here a is greater than 0 but less than 1, which means a is a fraction to begin with, and we get a decreasing function. Well, why is that? Well, again, it comes down to the fact that if you have 1/2 to the power of x, well, that's just 2 to the -1 x, which means it's 2 to the -x. So you're actually starting with 2 to the -x. So if you throw a negative number in there for x, you end up with a positive exponent, which explains that. And if you throw a positive number in there, you end up with a negative exponent, which then converts back to a fraction. So you can see we're coming down. And what you might notice here is this one is a reflection in the y-axis of this one, because that is what a fraction as a base looks like. So you can see the negative is in with our x value, which if we jump back to section 2, was a transformation that is a reflection of our x values. So let's practice graphing a couple of these. Now, it's super helpful when graphing exponentials to identify points on your graph and transform them just like we transformed in section 2. Now, one thing you'll notice is we have our horizontal asymptote at our x-axis. But if you remember our transformations, what's happening here, right? This is a vertical transformation. I'm just going to write shift down, right? So not only does our whole graph move down, but our asymptote moves down as well. And it's helpful to write that in. So our asymptote has now dropped to here. And then the rest of our graph is going to transform down. But what else happens, right? Think about this. This is a decreasing function because I have 1 over 4x. But if I change that to 4 to the -1, now technically that's not a fraction anymore, so you would think, oh, now it's an increasing function, but it isn't, because remember, that's just 4 to the -x. So I have two transformations happening here. All my y values are dropping down 3, and all of my x values are getting reflected. So just look at the points you have. 0, 1, nothing happens to my x value, but my 0, 1 drops 3. So it drops down to -2. But then all my x values get reflected. So 1, 4, right? 1, 4, my y values drop 3, so I'm going to end up at 1, but then my x values change sign, so -1, 1. So I'm actually right here. And then our graph will continue up, and it's to the power 4, so it's going to go up relatively quickly. So that's enough for your graph. You can just kind of come down, you go through this point, we go through there, and then you know where you're going to get infinitely close to your asymptote. And for this is enough. It's the general behavior of your graph. All right? So obviously, we're bringing transformations back into logarithms and exponentials now. So now we have the original function of f of 5x, and you'll notice we have points 0, comma 1 again, and we have 0.1, comma 5. And we'll use that to help transform. Because what is happening in my transformation here? The negative in front, remember, is a reflection of my y values. And then I'm also going up 3 vertically. And then in here, it means I'm moving the whole graph to the right 3. So let's do that with our asymptote and our points. So my asymptote is going to go up 3. So my asymptote is going to end up here. And now my point 0, comma 1, well, my y value gets reflected, so it becomes 0, comma negative 1, and then goes up 3. So it's going to be 0, comma 2. So I have a point at 0, comma 2 at this point, but remember that we need to also transform our x value. And our x value is going to go to the right 3, so this point ends up at 3, comma 2. So this original 0, 1 is now at 3, comma 2, is a point here. And then what happens to my 1, 5? That'll be enough. Well, so the 5 gets reflected, so it goes to negative 5, and then it goes up 3, so it goes to negative 2. But then I got to transform my x value and go to 4, comma negative 2. So I get the point at there. So this graph is going to go like this, and then it's going to get infinitely close to my asymptote. Now you might be thinking, well, we could also calculate my horizontal or my y-intercept, and you could. Remember, that occurs when x equals 0, but you're calculating this. So 5 to the negative 3, well, that means 1 over 5 to the 3. So that's negative 1 over 125 plus 3. It's going to be a very small number. So it's not really necessary at that point. Like really small number, just less than 3, right? Because we add 3. So general behavior of the graph is what we're looking for here. Plot some points and do your transformations like we did from section 2. Okay, now next thing we got to look at is how do we apply exponential work in the real world? Well, a big one has to do with money, compound interest. Other than annuities, compound interest is the way to go. This is either the best thing in your life or the worst thing in your life, depending on whether or not you are borrowing or are investing. Now, we've looked at this in other grades, but let's just do a reminder. A is your final amount. P is your principal, and your principal is the amount of money you have either invested or borrowed. For this example, we are investing. R is our interest rate as a percentage. N is our compounding periods. So that means how many times is the interest applied to our principal. And then T is time in years. So what information do we have? We want to know, find the interest. Okay, so interest. Well, interest is equal to your new amount minus your starting amount. So $8,000. So P equals 8,000. R is 8%, which is 0.08. It's compounded daily, which means 365 times a year, and time is 7. So we plug this all in color by numbers. A equals 8,000 times 1 plus 0.08 divided by 365 to the power of 365 times 7. So here's where you get really good at using your calculator, and you end up at 8,000 times 1.00022. I would carry that number in my calculator rather than rewrite it at every step, but I'm just demonstrating to you what happens. Remember, now you do the power first, then you multiply by 8,000, you end up with $14,004.52, give or take a few cents, depending, maybe a couple dollars, depending on if you round it or not. Try to not round, do the whole thing in your calculator. So if that's our A value, then we subtract our principal from our A value, so 14,004.52 minus our investment. How much interest did we earn? $6,004.52. Not bad. You earned almost your entire investment in 7 years. Compound interest is amazing. So here's another one. What initial investment is required to become a millionaire in 30 years if you receive 11% interest? Now that's very good interest, and compounded monthly. So what do we know here? We know that our compounding period is 12. Our time is 30 years. Our A value is a millionaire, so $1 million. Our p-value is what we're trying to find out, and our r value is 11%, 0.11. So again, we're now going to plug this into our equation, but we are going to have to do some algebra here. So 1,000,000 equals principal times 1 plus 0.11 over compounded monthly 12 to the power of 12 times 30. So we'll do a little bit of number crunching here, and we get 1,000,000 equals principal times 1.0092 to the power of 360. Now, I would divide both sides by this and then crunch the calculation at the very end. So you are doing 1,000,000 divided by 1.0092 to the power of 360, and the principal comes out at 36,999.25. So keep that in mind. If you have an additional $37,000 on around, you're good to go. Okay, so that is compound interest. Now, let's look at something that's called a growth decay equation. So there's two ways to look at this. One of them will make less sense until we do logarithms, but I'll show you both anyways. And this stuff is all another way of looking at exponential growth, but particularly this is used in exponential decay. So things like radioactive decay of isotopes is often used regularly. So this can be a little tricky because you got two exponents for time, so bear with me here, okay? Now, A is your final amount, so the amount you have left of a substance. A with a little zero, we call that A naught. It's your original amount. X is your growth decay value. Now, the little t is the total time that remains, and it'll kind of make sense when we're done here. And then big T is the time or growth of decay. So, look at this example. The half-life of Herlarium-239 is 45,000 years. So that is the time of growth or decay. So big T is 45,000 years. How much of a 3-gram sample will remain after 2,000 years? So that is this part, time that remains, right? So baby T is 2,000 years. And now we're looking at what's x. Well, x is our growth decay value, and if it's half-life, it means x is a half. And then my original starting sample, A naught, was 3 grams. So now it's color by numbers. I'm going to be looking at a final amount of 3 times 1/2 to the power of 2,000 over 45,000. So this is where you get good at using your calculator. Roll this through, and we get A equals 2.91 grams. So let's look at the application of this, okay? You have a radioactive isotope, and its half-life, which means it becomes half as radioactive, is 45,000 years. And we're only wearing down to about a 2.91 gram sample after 2,000 years. That's crazy. So we shouldn't dispose of radioactive waste all willy-nilly because it's going to be around for a long time. So keep that in mind when you see things like half-lives and radioactive decay. Let's do one more and I'll introduce you to the other equation. Now the difference between this equation is we have the constant E and we have a letter K, which is our proportional constant. And you need to actually solve for the proportional constant before you can do that. Now this isn't going to make sense to you necessarily unless you've seen this before until you get into logs, but then you'll see how we use it regularly. So first thing is we know again that A is 3, A is what we want. A naught is 3, but I only have one time this time, right? So what's my time in this scenario? In this scenario, my time is 45,000 because that's how long it takes for the half-life to occur. And then what else we got? E is a constant. It's on your calculator. And then K, we don't know. So before we have two unknowns here. So we can't actually solve for A until we solve for K. So how does that work? Well, we get the fact that since it's a half-life, we can say that, okay, well, my final amount will be 1.5 because that's how long the half-life, the proportional constant K will give me if I'm talking half-life. So I get E to the K times 45,000. Now divide both sides by 3 and you get 0.5 equals E to the 45,000k. Now, in order to do this, we take the natural logarithm of both sides of the equation. So, and again, we will do this in the later sections, but I wanted to show you this equation. And the natural logarithm of the constant e is just 1. So what we end up with here is we end up with the natural log of 0.5 is equal to 45,000 k. So then that means k is equal to the natural log of 0.5 over 45,000. So now you've solved for k. Don't worry about crunching that number. You have a value for k. And what you do now is you plug that into our equation. This one here. But now we have our final amount is equal to our initial amount, e, and now k is the natural log of 0.5 over 45,000. But this time our time is 2,000 because now we're figuring out how much we have left after 2,000. You can see the other equation is quite a bit easier at this point because we're using a lot of stuff we haven't been introduced to yet. But you'll see that what you end up with is the exact same result. So remember, this is k. I won't recrunch those values. You plug all this into your calculator, and again, that's where you learn to be good at your calculator. You get the exact same answer, as you should. So that's two ways to use applications of exponentials. What we're going to look at as we move through chapter 5 is exponential equations versus their inverse. If you remember inverse functions from section 2.5, their inverse function is a logarithm. So we're going to look at those as we move through section 5, and it's going to be nothing but enjoyable. All right, thanks for watching. See you next time.